So I'm Debolina. I'll be talking about scheduling of elastic message passing applications on high performance computing systems. So I'll be talking about motivation, some literature review, our objectives, and then our results and analysis. So what is actually an elastic application? According to Peterson's, parallel application can be of four types, where rigid and moldable applications, they do not change their resources during execution, but malleable and evolving application can change their resources during execution. For malleable application, the change is initiated by the system, and for evolving application, the change is initiated by the application. In this paper, we are going to talk about malleable and evolving applications as elastic applications. Current resource management systems for clusters primarily support rigid and moldable applications only. They do not support any malleable and elastic application, malleable and evolving application. So why do we need elastic applications? Like we have rigid applications and moldable applications. So what are the necessity of this elasticity? So the first thing, if we look around, many of our today's application, they are actually dynamic and they are event and data-driven applications. For example, we can talk about our healthcare monitoring wearable devices. So these devices, they monitor our heart rate, they monitor our blood pressure and many other things. So when there is no anomalies, these applications, they do not need to do a lot of things. They just need to do the monitoring. But if there are some sort of anomalies, maybe in the heart rate or maybe in the blood pressure, then they need to notify some doctors and then maybe they need to call 911. They need to call some emergency contacts and something like that. So this type of applications are like event and data driven. They do not have to do a lot of work at any moment, but when some event or something occurs, they need to perform a lot more activities. So these applications by nature are elastic. To handle this sort of applications and to efficiently use the resources, we actually need elastic applications. Then, as the number of components in high-performance HPC systems are increasing, so it is the chances of failing a component is also increasing. So what happens when a component fails? Then that applications actually shut down and the work that was going on is gone totally. But if we have elastic application, then maybe in spite of shutting the entire application, we can shrink the application, and then we can actually, the application can continue with lower amount of resources. And when the system is again up, then the application can again expand to the available resources. So elastic application actually helps in proactive fault tolerance. Then we can also offer design some flexible economic model for user and also the resource providers. Maybe if some mission critical application comes to the resource provider and says, let's say we need this amount of resources at this time, the resource provider can sell these resources to the user at a higher rate by shrinking another application. And the application it is shrinking, they can offer that a lower price. So a more flexible economic model can be used for user and resource providers. And last but not the least, elastic application actually improves application and system performance. There are lots of papers that have proved this, and we would also show the same results in our study also. So what are the challenges of having elastic applications? The first one is programming model, as the programming model of elastic applications, as they are going to expand and they are going to shrink. So their programming model is going to be different from the programming model for rigid application. So we need to have a programming model to model all of these applications. Then we also need system support. The system needs to maintain communication. We also need system support and resource management support. The resource management needs to maintain communication with the application, and message passing libraries like MPI, they should have enough resources so that the application expand and shrink, and also can communicate with the resource management. So there are some proposed programming framework for malleable and evolving application. One of the major flaws of this proposed framework is there is no very good way of shrinking an application. There are some ways for expanding an application, but there are like shrinking an application is like pretty hard. And if we talk about RMS support, CMIX actually have some proposed APIs using which application can actually communicate with the resource manager for expansion and shrinkage. But these APIs are under work. These are just proposed APIs right now. They do not have any implementation of this. And also there are lack of scheduling algorithms because scheduling elastic applications along with rigid applications requires different scheduling algorithms, because the scheduler needs to decide that if there are like the scheduler needs to decide which application to expand, which application to shrink, and when to do what. So there are also lack of scheduling algorithms. There are some proposed algorithms that actually schedule malleable jobs. There is one algorithm that actually schedules evolving job and malleable job along with rigid job, and one application that actually schedules malleable and evolving job along with rigid job. So where are the research gaps in this area? The first one is programming model. As I said, there is no very well specified programming model for elastic application. There is lack of resource management support. CMIX has some approaches, but they are still like no proper implementation of that is there. And then there is also like lack of support from massive passing libraries. MPI has a little bit support called for expansion, but MPI ComSpawn is not very popular. It has lots of loss of itself. And then the shrinkage is always there, like nothing very good regarding shrinkage. And in spite of scheduling algorithms, there is lack of scheduling strategies for scheduling both malleable and evolving application. And then there is no thorough study on candidate or victim selection policy. By candidate and victim, I mean which selecting the application to shrink, like which application to select to shrink. And then there is no study on impact of workload characteristics on performance, like on which workload I should think that I should have some malleability, some elasticity here, or I should not, like I don't require anything. Like what I have, I'm fine with that. So there is no study on impact of workload characteristic, like how workload actually impacts all of this performance when there is elasticity in the workload. So here in this paper, our main objective is to investigate the impact of different scheduling algorithms and candidate selection techniques, and also evaluate the impact of workload characteristics on performance. So we are going to answer like two research questions. The first one is how significant is the difference in performance between different candidate selection techniques for shrinkage and expansion, and how workload characteristic contributes to the impact of elasticity. So so we have calculated in our application model, we have calculated along with the runtime changes, we have also considered and modeled the cost of expansion and shrinkage. So expansion and shrinkage actually involves data redistribution cost among the new processor, and also synchronization cost, because an application cannot expand or shrink at any arbitrary point of execution. They need to come to some synchronized state, and then they can actually expand and shrink, and other overheads such as process creation and termination cost, etc. So data redistribution cost and synchronization cost together, we are going to call them adaptation cost. And then we have modeled it as like if each elastic job has a minimum and maximum allowable resources, they can actually function within this limit. So our main scheduling algorithm, the priority is given to, highest priority is given to evolving requests, and then pending job, and then running malleable jobs. These priorities can be altered very easily. So as our highest priority is given to evolving requests, so first the scheduler actually schedules evolving requests. So if it is a shrinkage request, then it's just go ahead and shrink the job. And if it is an expansion request, then it first try to allocate idle resources And if enough idle resources are not found, it shrinks malleable job to allocate resources. And then the second priority comes, it tries to schedule pending jobs. So it first try to schedule the pending job with the proposed allocation if enough resources is found. And if the job is malleable and enough idle resources is not found, then it's try to schedule the job with the minimum resources. As I have talked about that every elastic application has a minimum and maximum allowable resources. And if this is also not the case, then it shrinks running malleable job to allocate resources for it if enough resources is not found in the second step. And to select how to select a malleable job for shrinkage, we are going to talk about it in the next slides. And in the third part, it comes that it expands running malleable job with the highest runtime if there are idle resources, like after performing, after scheduling evolving requests and after scheduling pending jobs, if there are idle resources in the system, it actually expands running malleable job. And in this case, it doesn't matter which job actually it is expanding. It is always going to increase the system utilization. So it actually picks the job that has the highest runtime so that to satisfy the application point of view. And then to select the shrinkable malleable job, we actually have three techniques. So the first one is, we call it default, because it just sorts the running malleable job according to candidate selection. Candidate selection I'm going to talk about in the next slide. So it sorts the running malleable job according to some sort of priority, and then it picks the top one from the priority list, and it shrinks the malleable job until enough resources is not found. So the second one is, the second technique is called application. It has one difference from the default one. Default just picks the malleable job and shrinks it. And for this application, before shrinking it, it looks at the application state. That's why its name is like application. So it just looks if a job is going to end in next T seconds, then it does not shrink anything. It just waits for the job to end so that this many resources can be used before scheduling a new job. The rest is very similar to default. And the third one is basically system. So it looks at the system perspective before shrinking any job. It just looks that if utilization is a certain, if the system has a certain percentage of utilization, it does not shrink any job further because it has a satisfied amount of utilization. So it does not actually try to increase the overhead anymore. So it does not do anything. It just returns and waits and if not, it's just very similar to the default one. So for candidate and victim selection technique, as I have talked about before, like which malleable job to pick for shrinkage. So random is very straightforward. It just randomly picks a job. From there, it does not, so it basically has no priority. It just randomly picks a job. And then the second one is adaptation. I have talked about adaptation cost. It's the data redistribution cost and the synchronization cost together. So the job that has the lowest adaptation cost is actually shrinked first. Then expansion, the job that has the highest number of previous expansions, that is actually shrinked at first. Gain is basically, say for example, at the beginning, each job has 0 gain. And at some point, a job is shrink and it gets P more resources. Then its gain becomes 0 plus P. And say, for example, after some time, the job is actually shrink and it loses Q more resources. So its minus Q is added because it loses resources. So its gain currently becomes P minus Q. So the job that has the highest gain is actually picked for shrinkage. Resources is as a job has a minimum amount of resources. So when a job is running, say for example, a job is running on 10 processors and its minimum resource is 5 processors. So it's in this, it has 5 resources to shrink. So in a similar manner, that has the job that has the highest number of resources available to shrink is actually shrinked first. And time is basically the job that has the lowest runtime, lowest remaining time is shrinked because it's not going to, because it's going to impact the overall performance the less. Now, to try all of these techniques and all of these algorithms, we have used a discrete event simulator to simulate all of these algorithms. And we have picked some workload, like we have picked 4 real workload and 1 synthetic workload. The real workload is basically taken from Parallel Workload Archive. The LLNL and the KIT workload, the first 10,000 jobs from there is considered, and LLNL shrunk and KIT shrunk are basically a shrunk version of this workload, where the shrunk version is actually, in the shrunk version, we have shrink the interarrival time of the work so that the workload is higher. So the difference between LLNL and LLNL shrunk version, or KIT shrunk version, is basically the shrunk version has higher load, and the synthetic workload is generated using Downey's model. So now all of these workloads are rigid workloads. We have to create elastic workload. We had to create elastic workload from there. So we have, for every workload, we have total 10 elastic versions with 10%, 20%, and 100% of elasticity. So for 10% elasticity means that 10% of the total jobs are elastic and jobs are chosen randomly. And then we randomly select X% job to be malleable and X% jobs to be evolving into X% elasticity. This means that when we have 20% elasticity, 10% of the jobs are malleable and 10% of the jobs are evolving. Now, if I look, as we are going to analyze the workloads, what's the major difference between the workload? The difference between the two rigid workloads, I have already talked about. The difference in the shrunk version is basically that the shrunk version has higher load, and there is also a difference between the real workload and synthetic workload. So the two real workloads are pretty similar. So in many cases, in the future in the presentation, I'm going to skip the results of one of this because they are like very similar. So the difference between a real and a synthetic workload is basically the distribution of job. In the real workload, job distribution is not uniform, but in the synthetic workload, the job distribution is actually uniform. As the job distribution is uniform, also the distribution of elastic job is uniform. In this figures, we can see that the number of elastic job at 50% elasticity, which is blue, we can see that in terms of synthetic workload, this distribution is uniform. So there is always some elastic applications available for expansion and shrinkage, but this is not the case for the real workloads, and all the real workloads are similar. So I'm skipping the results of the others. So for evaluation, we have used average turnaround time and system utilization. So average turnaround time shows the performance from applications perspective and system utilizations from system perspective. So this is the result of average turnaround time for KIT workload with different algorithms. We can see that with increased elasticity, performance improves, and also, as I have mentioned before, that elasticity actually improves performance over rigid applications only. It also states the same fact. And then this is the result of system utilization with KIT workload. Here also you can see the same similar manner, similar results, and it also performance always improves with elasticity. The dotted line is actually shows the performance of workload with only rigid jobs. This is the result of KIT shrunk workload with different algorithms, and you can see that it shows the average turnaround time, and we can see that average turnaround time improves with increase of elasticity mostly, but it's saturated at a certain point. And also this is the result of system utilization. Here also we can see that performance improves with increase of elasticity, and also like we can see that performance always improves, is always better than with performance with rigid job only. This is the average turnaround time of LLNL workload with different algorithms. And this is the system utilization with the LLNL with different algorithms. They have, like, as I talked about before, they are very similar in the manner of KIT workloads. This is the performance of LLNL shrunk, and this is the performance of system utilization with LLNL shrunk workload. Now we are going to see the performance of synthetic workload. So this is the average turnaround time of synthetic workload with different algorithms. Here, one thing we can see that the performance in case of synthetic workload, the performance improvement is always kind of linear with the increase of elasticity. As we have talked about before, the job distribution was uniform, so there are always some jobs available for expansion and shrinkage. So this is mainly the reason for this performance increasing constantly with the increase of elasticity. And in case of utilization, we can also see the similar fact. So in this table, first we can see that it's a comparison of KIT and KIT shrunk. As we remember, the difference between these two workloads are basically the shrunk version has higher load than the original version. The performance of NL is similar, very similar. That's why I'm skipping it, and I'm just showing the result with default. The results with other algorithms are also very similar. So what I'm doing here is I am trying to show the maximum difference between two candidate selection algorithms and at which point that occurs. So we can see that for KIT workload, the maximum difference in average turnaround time was 5.7% improvement for gain, and for the shrunk version, it was 2.84% improvement. And for utilization for KIT, the improvement of performance was 10.25%, but in the shrunk version, the improvement of performance was just 1.13%. And this pattern was shown for every algorithm and every cases. So we can say that from here that if we increase the load, it does not the difference of performance between different candidate selection algorithms actually become insignificant. So which candidate selection I'm choosing actually does not matter that much. We can just randomly pick any of the candidate selection algorithm. If the load is high, how I'm choosing the malleable application actually does not matter. Choosing anything will actually improve the performance. And also only the performance of synthetic workload improves constantly with the increase in elasticity amongst the 5 workloads. The reason behind this was the uniform distribution of the job and the uniform distribution of the elastic jobs mainly. So we also tried to achieve, like in none of our cases, we could achieve actually 100% utilization. So we ran an experiment again to and try to achieve 100% utilization. We took the KIT workload and we set the minimum amount of resources to be 1 and the maximum amount of allowable resources to be equal to the total resources that the system has, and try the same algorithms again for utilization, and we could see that even with 100% flexibility, that the minimum can be 1 and the maximum can be the total resources available in the system, we cannot achieve 100% utilization. And also improvements actually kind of saturates after a certain point of elasticity. So above that, if we increase the amount of if we increase the number of elastic applications in the workload, it actually does not matter. The gain we are getting, the improvement we are getting, is constant. So for not getting 100% utilization, the reasons are like, even with 100% flexibility, there can be fragmentation because there may not be evolving application available to expand or shrink. And then again, we are getting the performance is actually also saturates after a certain point, because as I'm allowing it to be maximum, even if I increase, I don't get a lot of improvement after a certain point, because we are allowing maximum amount of resources. And also some fraction of utilization is actually lost in adaptation cost and in other overheads. So that's also another reason for not getting 100% utilization. So in conclusion, we can say that when the workload is high, the performance difference between candidate selection techniques does not matter, it's insignificant. And impact of elastic job depends on both the percentage of elastic job and the distribution of elastic jobs over time, because if the distribution is uniform, then you will get a constant improvement. And if it is not, even if we increase the percentage of elasticity, we are not going to get improvement in the performance. And even introducing 100% flexibility, utilization may not be 100% due to fragmentation and some loss in the overhead. And algorithm also, as we have proposed like many algorithms in all the cases, algorithm system gets the highest system utilization, and in most of the cases, algorithm application gets the lowest average turnaround time. And in terms of average turnaround time, our case study shows that game performs the best and random performs the worst in most cases in terms of candidate selection techniques. And in terms of utilization, random performs the best and resource performs the worst in most cases. And in all the cases, we have also reassured the already proven fact that even a low percentage of elastic job in the workload improves the performance. So we have some proposed future work. So we have not done any research on candidate selection for expanding job. Everything is for shrinking the job. So we want to do something in that. And as we have seen that utilization is actually reduced by some portion of fragmentation and some overhead also, we want to analyze more that how much is lost due to fragmentation and how much is lost due to overhead. And in our model, we have only considered processes to be resources. We want to consider all sorts of resources like memory and others as well. And also like some in the simulator, we have selected some parameters which are not optimal because say for example, there are some models, they actually tries to simulate that they try to predict what the runtime going to be of an application if it is running on a different amount of processors. We can use that to actually better getting the changed runtime after expansion of shrinkage. And that's all. So thank you so much for listening to me. Here are my references. Thank you. Any questions?
Thank you. I see some message in the chat. So Debolina, if you are interested, don't miss that. It seems like it's relevant to your work. And do you know the problem with this moldable elastic applications, I believe, is that these proposals have been here before, right? But somehow it's complicated to actually, implement these programming models in mainstream applications. So do you have some candidates? As you mentioned, not every application will be elastic, but some maybe it's time to give it a try. Do you have some idea which types of applications would suit this paradigm well?
Well, so I like to say that first statement, like first point of this study is we don't actually need to make like all the applications elastic because we cannot get good performance even making all the application elastic. After a certain point, performance actually saturates. And the second one is the scheduling algorithm also does not need to be like very complicated because like it doesn't matter if the workload is high, and involving and bringing elastic applications, the more proper situation will be when the workload is high, because otherwise we do not need elasticity. If we have like enough resources, then we can allocate the highest amount of resources that is required. And to select which applications to be made elastic, I will suggest that the application that has lower overhead, like that are very highly scalable, because those applications will not have much effect on shrinkage. So applications, those are like for the beginning, we can think of applications, those are highly scalable to make elastic. And I think that's a good starting point, like starting with something that is not too complicated and that is easy to implement.
So I would like to chime in. I think any kind of embarrassingly parallel application would be the best candidate, obviously. There are applications like many stencils type of application would actually work on that. And there are some simulation application. I think OpenSea, there was earthquake simulation, which considers each building individually based on a movement in the earth, very embarrassingly parallel, but very computationally intensive. Those type of application would be the first things. I think wherever the major challenge would be the data redistribution and any kind of dependency, so less dependency among the tasks would be the best thing to go.
That was actually the second part of my question, somehow related. So in this study, I believe you consider CPU as the resource that is considered, but do you have some idea how other resources would be influenced, like memory, GPUs, you know, stuff like this? Because that's another dimension of what must be scheduled, right?
Debolina.
Okay, sorry, I just thought that you are going to, okay, I'm sorry. Okay, so we also considered like other resources like memory in future, because say for example, I am shrinking a job, then I need to redistribute the data that was shared among all the processor, and we know like the memory architecture today is like getting complicated, so it's not like uniform. The memory architecture, if it's not uniform, it's non-uniform, then also we need to consider the memory, because the access of memory of each processor is going to be different. Because so if I'm shifting the memory from one processor and I'm shifting it to another processor, I need to shift the data to also some memory that is accessible to that processor where I'm shifting to. Because yeah, the more complicated the system becomes, the more complicated things we need to handle in case of memory also. So yeah, but also we can like, it's also like processor is actually the most significant one that we need to consider, because everything else is actually can be manageable and can be doable, because it's not changing in a sense, mainly because the time can be like accessing a memory which is located at a remote place can take some more time in computation, but that is actually negligible. And in big supercomputers, when the processors are also like very scattered, like one processor is here and another processor is there, we know the communication time is actually also like not that significant. Like if we assign processors that are close, like that are in the same core, and if we assign processors across different cores, the communication time between them actually does not matter that much. So memory is obviously like where there is not uniform memory. So there are actually things we need to consider, but also the significance of them is much lower than the significance of resources as processor.
No, I think in terms of scheduling algorithm, your degree of freedom lessens, it becomes a little more complicated, but the main observation, I think, still remains the same.
Yes.
One of the assumptions was the system is sort of homogeneous, which may not be true, but in many cases, the big systems are kind of homogeneous. So obviously, if you consider, so for example, GPU, memory, and other resources, and I think the same principle can be extended, just the scheduling algorithm, or in terms of freedom for the scheduler would be a little less.
Yes. So yeah, that's what we observe in today's big systems like Summit and everywhere. So we get pretty random nodes. Like if we submit a job to one of the supercomputers, we get pretty random node, and if we get a different set of nodes and different set of processors, our performance does not vary that much. So that's the insignificant part, but if we want to include it in future, but that is going to increase the complication a little bit, true, but not that significantly. It's not going to decrease or increase the performance. The understanding and the performance is going to be same.
Great. Yeah, I was not actually expecting some definite answer. I was just more like, that sounds interesting. What happens when You know,
Yes, it gets complicated, a little bit complicated.
yeah. So just it was just a suggestion. Okay, thank you.